Hello everyone, I'm Kushal Lodha, a graduate student at Korea Astronomy and Space Science Institute. First, I'd like to start by thanking organizers for giving me opportunity to present my work. Today, I'm going to talk about hints of dynamical dark energy and phantom crossing in the DESI era. The first part of the talk is based on dark energy supporting paper and is a broader collaboration-wide effort within DESI DR2 BAO analysis. And the second part of the talk, I'm going to talk about some physical mechanism through which we can cross the phantom divide to explain the trends in our data. What can we probe about dark energy? We can describe the dynamics using equation of state, W of Z, which is simply a ratio of pressure to energy density. In standard Lambda CDM, W is fixed to -1, meaning dark energy density remains constant in time. To allow for dark energy evolution, we can let W vary away from -1, often using popular parameterization like W0 WA, which has 2 additional degrees of freedom. Once we specify W of Z, we can integrate to obtain dark energy density as a function of time. You can plug that dark energy density into Friedman equation to compute the expansion history. It's important to keep in mind though, we do not measure dark energy density directly, but infer it from quantities like Hubble parameter or cosmological distances, which involve integral and double integral of equation of state. So any rapid variation in equation of state tends to get washed away when we look at the observables. How do we probe dark energy? We rely on 3 complementary observational probes. First is standard candles like type 1a supernovae. Second, we have large-scale structure surveys like DESI SDSS that provide us a standard ruler through baryonocaustic oscillation and turnover scale. And finally, we have cosmic microwave background from the experiments like Planck, ACT, and SPT. So if we start with the simplest case, Lambda CDM still does a reasonable good job of describing all 3 datasets overall. But if you look carefully, in omega m H0 RD plane, DESI and CMB constraints are already becoming noticeably discrepant. In DR2, this discrepancy stands at 2.3 sigma. But when you consider the latest combination of CMB datasets from Planck, ACT, and SPT, this tension further rises up to 2.8 sigma. So why lambda might be insufficient? The plot on the right gives us a basic clue. Different probes looking across different redshift ranges do not quite prefer the same amount of dark energy. This opens up the possibility that dark energy may not be constant, but evolving with time. To consider such evolution, we can add 2 degrees of freedom in the form of W0 WA and see what kind of a constraints do we get. So let's first start with DESI alone. What we find is that the DESI itself is not constraining enough to rule out the lambda, but it has a very well-defined degeneracy direction in W0 WA. The picture becomes much more interesting once we combine DESI with the CMB. What we see is the preference for this evolving dark energy now raises up to 3.1 sigma. In DR1, this used to be 2.6, but now it has crossed the threshold of 3 sigma. Finally, when we bring the type 1a supernovae, we obtain the constraints on the strongest constraint on the dark energy dynamics. Depending upon which supernovae compilation we use, the deviation from lambda ranges roughly between 2.8 to 3.3 sigma. Since last year, we also had 2 major updates on the supernovae side in the form of DS Dovocki and Union 3.1. These changes have brought down the significance down from 4 sigma to 3.2 sigma, but they also led to much better consistency across all 3 supernovae compilation. To better understand these constraints, we can take these contours on the right and convert them into redshift into function of redshift. On the top, we have equation of state W of Z, which goes from greater than -1 at low redshift to less than -1 at high redshift. This evolution is also reflected in dark energy density as a bump in the bottom plot. The peak of the dark energy density is roughly around z equals to 0.8. That is marked with a solid gray line. You can see it's the same point where W crosses -1. A dashed gray line shows the matter dark energy equality, which is slightly before the phantom crossing. Let me remind you, phantom crossing does not necessarily mean null energy condition violation. For that, your total equation of state has to cross -1. For more details, you can refer to the paper by Robert Caldwell and Eric Linder. Next, we look at the deceleration parameter Q of z, which tells us how the rate of cosmic deceleration changes with redshift. The dotted vertical line around z equals to 0.8 marks the point where universe transition from deceleration epoch to the acceleration epoch. Notice this is much before the matter-dark energy equality. W0WA model suggests that universe has started accelerating much earlier than predicted by Lambda CDM. However, if we look at the present epoch, we see the hints that the rate of acceleration might actually be slowing down. Rather than restricting ourselves to two parameter extensions, we can ask how many dark energy parameters do we need? We can test this by modeling our equation of state in terms of the Chebyshev polynomials. And depending upon where we truncate the polynomials, we can introduce different additional degrees of freedom. On the right, I am showing you the results for n equals to 3 with DESI plus CMB combination in orange and DESI plus CMB plus union combination in the blue. We can also explore giving similar freedom to the dark energy density directly. This even allows for negative dark energy densities. What we find in the bottom plot is a similar trends as we saw in the W0WA. We can perform this exercise for the different values of the n and plot how improvement in the delta chi-square relative lambda CDM changes with the number of free parameters introduced. We find that the improvement in the fit to the data saturates around 2 for equation of state and 3 for dark energy density. The black dotted line is shown here as a W0WA comparison in the delta chi-square plot. We can also take more agnostic approach and bin dark energy equation of state directly. Just to be clear, what we are binning here is a functional form, not the data itself. So instead of sampling W0WA, we can sample 4 bin values which are connected with smooth tan hyperbolic interpolation. Here on the top left, I am showing the results from 3 uniform bins with DESI plus CMB plus union 3 with W0WA prediction in the gray band. Our analysis finds 3 sigma deviation in the lowest redshift bin and overall trend consistent with W0WA. We can repeat this exercise with different binning schemes. On the right, I'm showing you the results for 3, 4, and 5 uniform bins. We have also tested wide range of alternative binning scheme that matches to have 1 bin per tracer, logarithmic binning. We have even tried giving similar freedom to the dark energy density directly. Even with all this additional freedom, we find that the quality behavior remains very, very similar. Another non-parametric approach we can use is a Gaussian process regression. Instead of assuming a specific functional form for W of C, we can use Gaussian process to draw the samples from the functional space. The Gaussian process is defined by a mean function, which in our case is lambda CDM prediction of -1, and 2 hyperparameters. The amplitude sigma f, which dictates how much our sample is deviating away from the mean, and the correlation length LF, which sets how smooth these samples are. This setup allows us to draw smooth W of Z from the prior distribution and test them against the data. You can think of it as marginalizing over a family of curves rather than parameters of your favorite model. On the right, we show equation of state reconstruction from the Gaussian process using DESI plus CMB plus union 3, and we find our posterior shown in the blue broadly consistent with trends seen in the orange curve showing CPL constraints. So by this point, hopefully I've convinced you that this deviation is not just an artifact of parameterization, but a genuine trend in the data. Next step is to use this agnostic reconstruction as a guide and ask which physical model can actually account for such trends. One of the most widely discussed possibility in the literature is quintessence, where dark energy comes from a rolling scalar field. As field evolve in its potential, the pressure and energy density change with the time, giving a dynamical equation of state as shown in the middle expression. As you can notice, for the canonical scalar field, equation of state is bound between -1 and 1. Here we consider a subclass of quintessence model where scalar field is initially frozen due to the Hubble friction, meaning your equation of state is -1. But as universe expand, field thaws away from the constant, giving dynamical dark energy. Rather than focusing on a specific potential, we use a generic parameterization shown in the top right equation that can capture this general behavior. There are two free parameters, W0, which tells you what is equation of state at present time, and a P parameter which indicates how steep is this rise from -1 to W0. As an illustrative example to show that this parameterization work, we have converted a dynamics of axion-like field into W of z, and you can see that this is a very similar form what we get when we actually consider constraints on W of z from DESI plus CMB plus union 3. In the bottom plot, I'm showing you how the posterior areas differed if you change from union 3 to DESI DR5 or Pantheon plus combination. To test whether data favor phantom crossing, we can compare thawing dark energy model, which is restricted to W greater than -1, with W0 WA. The table on the left shows W0 WA consistently give a better fit by about 7 to 10 chi-square compared with quintessence. A quick caveat, these are non-nested model, so Wilks' theorem does not apply and there is no simple frequentist model comparison. Another useful way to see the same comparison is through reconstructed expansion history. Here I'm plotting h of z relative to best fit lambda CDM model. In the phantom crossing case, h of z develops a clear non-monotonic bump. By contrast, in the thawing case, h of z rises but then settles to a constant offset with no turnover. So while dynamical dark energy signal shows up roughly at 5% level, establishing phantom crossing is much more demanding because it requires the full shape of h of z to be better constrained than less than 3%. For a decisive detection, you really need both high and low redshift information. Low redshift information will constrain the shape of this feature, while high redshift probes will tighten the uncertainty around omega matter. So a combination of them can detect such phantom crossing. So if we take a data at a face value, how can we achieve such phantom crossing? Over the last couple of years, several interesting papers have shown concrete ways it can happen. Broadly speaking, we can group them into three classes, each obtained by relaxing one key assumption in standard framework. In the first, if we relax the assumption that dark energy is not interacting with any other species, we can allow for coupling with dark sector. In the second class, we can relax the assumption that gravity is described by general relativity and allow for non-minimal or modified coupling. And finally, in the third, we can revisit our assumptions about the vacuum that can lead to non-standard vacuum scenarios. So let me start with the first possibility, where dark energy is allowed to exchange energy with dark matter. This is introduced through an interaction term Q, which modifies how both matter and dark energy density evolve as a function of redshift. This extra degree of freedom can shift effective dark energy equation of state up or down depending upon the direction of the energy flow. So let's say if you start from a thawing model, which on its own cannot cross W equals to -1, but with the right sign of the interaction, one can pull effective equation of state across the phantom divide. At the same time, because matter sector no longer scales as 1 plus z cube, this leaves a visible imprint in the growth of the structure. We are working with Nisha Kamble at UT Dallas to constrain such models with DESI DR2 full shape. So the second possibility is to relax general relativity itself. Christian Garcia Quintero is leading the DESI full shape analysis to test the modified gravity models and see how far DESI can push this constraint. Compared with our year 1 analysis, we are now incorporating several important improvements. This includes adding low redshift picular velocity measurements, bispectrum information from DESI DR2, and beyond EDS kernel. As the plot shows, This beyond DDS correction become really important at high K as they can change the power spectrum multipoles at 5 to 10% in the modified gravity scenarios. Finally, the third possibility is to revisit the assumptions we make about vacuum itself. In these scenarios, originally proposed by Leonard Parker and collaborators, vacuum undergoes a phase transition once the Ricci curvature reaches a critical value. Before the transition, R follows the standard matter-dominated evolution, while after the transition, it is effectively pinned down to a constant value. In such standard vacuum metamorphosis scenario, effective equation of state always stays phantom. Here we introduce the decay of phantom into a radiation-like component, which is parameterized by gamma, that effectively uplifts our equation of state, allowing it to cross the phantom divide line. Vacuum decay by itself already does a good job of reproducing late-time trends preferred by the data. But once we consider a joint fit with the CMB, this is no longer enough on its own. What helps is adding one more degree of freedom in the form of pre-transition vacuum expectation value. This effectively gives a model additional smooth dark energy component before the phase transition. The plot on the left shows effective equation of state, which starts at W greater than -1, slowly transitions into the phantom divide, but then comes back to W equals to -1 after the phase transition. The table on the right quantifies the fit in terms of the delta chi-square relative to lambda CDM for different dataset combinations like DESI, DESI plus CMB distance prior, DESI plus DS Dvoke, and all three datasets combined. Before conclusion, let me end with one broader point. All three classes I just discussed look fairly degenerate at the level of background expansion, but they may still leave a distinct signature in the growth of structure. So growth information could ultimately help us tell the scenarios apart. In that respect, upcoming DESI analysis of redshift space distortion and peculiar velocity will be crucial for stress testing these classes. To summarize, we see a strong hints of dynamical dark energy in the recent data that are very well captured by W0 WA parameterization. Form independent reconstruction align very well with trends seen in W0 WA. Current data prefers model with W crossing -1 over non-minimally coupled scalar fields with rapid time evolution. If we take data at face value, we have strong motivation to explore the model classes that can cross the phantom divide. Growth information from upcoming DESI analysis and other stage 4 surveys could be a key to distinguish between such scenarios. Thank you for listening. Looking forward to hearing your comments and questions in the discussion section.